Two of the largest scientific experiments in particle physics today study proton collisions at the Large Hadron Collider at CERN, ATLAS and CMS. They use general-purpose detectors to look into the products of this collision with the hopes of finding new physics, be that new particles or new information on the ones we already know about. From these experiments, the most well-known discovery is that of the Higgs boson found in 2012. The Higgs boson is very important to make the standard model of particle physics work. This theory describes the interactions between the elementary particles mediated by the fundamental forces, electromagnetic, weak and strong. According to the standard model, the Higgs boson is responsible for giving other particles mass. Since its discovery, the boson's characteristics have been investigated. The Higgs boson cannot be detected directly, but we can infer its properties by detecting its decay products as well as the particles it interacts with, which can be seen by the detector. With this data, we hope to measure the properties of the Higgs boson and see if they agree with the standard model predictions. If they don't agree, it could signal the presence of new physics that could help shed some light on the mysteries in our understanding of the universe. One of the biggest open questions not explained by the standard model comes from the fact that, according to the theory, the Big Bang should have produced the same amount of matter and antimatter. Antimatter is in all ways equal to matter, except for the fact that antiparticles have charges opposite to the corresponding particles. This symmetry is not in accordance with observation that shows there is, of course, more matter than antimatter in the universe. Among the conditions that need to be met to account for the observed asymmetry is a violation of charge and parity, or CP. If CP is conserved, it means that the particle interactions should be the same if the particle charge is inverted and its position mirrored. According to the standard model, CP is mostly conserved. The sources of CP violation the model does account for are not enough to explain the asymmetry, so we need to search for new physics that fills this gap, especially at the high energies we can now access through the Large Hadron Collider. Some theories beyond the standard model suggest that the source of this violation can be found in the anomalous interactions between the Higgs boson and other particles. So studies of the Higgs boson can be used to test such theories and potentially help solve this mystery. The work I am developing is included in this area of research, using proton collision data from the ATLAS experiment. In particular, I am studying the coupling between the Higgs and the W bosons in a process resulting in a lepton, a neutrino, and two bottom quarks being produced. More specifically, the focus is in studying a new observable sensitive to CP odd interactions, where CP is not conserved, with the goal of being able to find evidence of the symmetry breaking mechanism.